Hi, my name is Kit Franson and I am the Customer Training Manager in the CDS group at Trane. Today we will be going over a Trane 700 load design output interpretation. We'll go through a few examples and I will highlight some common reasons for viewing load output. Specifically, we'll do a general overview of load design reports and then take a look at outputs of an example I created of a 5-zone model. With this example, we'll learn how to use the outputs for troubleshooting issues such as uncharacteristic system coil sizes or airflows, learn how to use the outputs to size HVAC equipment for selections, and then discuss benefits of certain reports for optimizing load design to reduce costs of a project. We'll cap the video off with output considerations that discuss how to properly apply a load design model to real-world applications. To start it all off, let's first talk about all the key load design reports. All these reports are located on the Design Reports tab, located in the View Results section of the program. There is also a Detailed Reports section in View Results as well, but we will not be touching on those today. Those reports break down envelope and internal loads even further and are more granular in detail. We will venture into some of these reports later on in this video. Now we have an idea of what reports we can view. How can we apply them to a real-world example? Using Trace's new file wizard, we can create a 5-zone office building located in La Crosse, Wisconsin that is 62,500 square feet and is 40% glass on all exposures. The building will be one floor with 4 exterior zones as well as one interior zone with an internal geometry of 12 feet for floor-to-floor height. There will be standard office internal loads, and the construction will be better than the Section 5 minimum insulation values for walls and roofs, as well as the minimum glazing performance in ASHRAE 90.1 2010. From a system perspective, the entire building will be served by a single rooftop unit that is a VAV system with 30% minimum damper position and will bring in the required outside air to meet ASHRAE 62.1 2007. In advance of this video, I created this model using the new file wizard and made proper adjustments to the envelope construction as well as the ventilation rates. If you are interested in learning how to use the new file wizard, please watch our other YouTube video that explains how to create a quick block building for analysis. Since the file is created and the rooms are assigned to our RTU VAV system, we can now click the Calculate and View Results button, run the file, and view our load output design results. There are quite a few reports, which I talked about in the earlier part of this video, that can view the building loads in a variety of different ways to efficiently determine A, the components of the building that drastically impact the total outputted coil load, and B, the fan and coil sizes for equipment within the building. So what we'll do is we'll take a closer look at a few reports that I feel very helpful in the troubleshooting and optimization process that typically occurs in load design. With Trane 700 load design reports, there are some reports that can be more important than others. In this case, we'll focus on 3 reports here that are frequently used by our customers: the checksums, psychrometrics report, and system component selection report, which can be used for a variety of interpretations. When doing a load design analysis, we typically see our customers looking for ways to reduce load on their systems, troubleshoot results, or even size their equipment. Load reduction is going to be more granular as we will look at line-by-line load outputs. This is where we need to introduce energy conservation measures on either the envelope, system, or internal loads to reduce the capacity of the cooling or heating coils. If we are troubleshooting, this is where we can determine if the end results make sense and work backwards to determine what is driving certain results. Even if we're focused on energy and not even load design, we can still use the load design reports to even diagnose issues such as high energy usage, which can sometimes be related to the equipment size. Lastly, we can look at specific reports to determine how many systems or equipment we should be incorporating in the building. So what we'll do today is take a look at the breakdown of loads for this building system in the checksums, how the coil and fan are sized through psychrometrics, and verify the size of the equipment through the system component selection report. To start off, let's take a look at the checksums so we can look at a breakdown of building and system loads. I'll mention right away that these reports are not meant for equipment sizing, so please refer to the system component selection report for equipment sizing. In this case, we'll open up the system checksums for the cooling coil information since we have a VAV system and the cooling coil is located on the system level. This report is going to give us a breakdown of cooling and heating loads at coil and space peaks, in addition to some basic sizing information. We can start by taking a look at the cooling coil peak section here, which is going to show us a breakdown of envelope, internal, and system loads at the respective peak hour. You'll notice here that we also have this done on the cooling space peak, which is just sensible loads during the hour at which the space peaks. On the cooling coil peak section, this area of the results is useful because it can show us the breakdown of loads in the plenum as well as in the space. Trace assumes that the space and plenum are separate thermodynamic volumes and a heat balance is performed between these two spaces. What we can determine from here is the distribution of loads in the building and how much of an impact it can have on the resulting supplier dry bulb temperature and CFM. This could be helpful for troubleshooting. If we have high plenum loads and low space loads as an example, we could potentially have a low CFM per ton, which may not be realistic. So if we look at the details in this particular section, you can see from the output that the largest loads on the system are from the internal loads here, which is 43%, then the ventilation load, which is 23%, and then followed by the roof conduction load. As an example, we can use this information as a way to optimize our system type. We might be able to add in maybe an energy wheel for this ventilation load, or potentially even reduce internal loading through LED lighting. If we move on, you will also see a heating load calculation performed, which is using the worst case outside air winter dry bulb condition and assuming that there are no solar loads. Additionally, we'll have a load breakdown based on space and coil peak. Next, we can take a look at the cooling space peak column. We can use the sensible cooling load total at the bottom here to validate the main airflow calculation through using the sensible heat equation, which is Q is equal to density specific heat product multiplied by the supply CFM and then multiplied by the temperature difference between the space to the supply air. You'll see to the right that we have our resulting airflows, which I'll touch on in a little bit. The total sensible cooling load down here might be either from a peak load or block load depending on the system type. VAV systems have the fan and coil loads typically calculated based on a block methodology, as the fan is usually allowed to modulate its airflow as the load decreases or increases for the system to properly condition the spaces. Constant volume systems is continuous air volume and have to be sized on the peak airflow and load of every space, as the airflow cannot be shifted to conditioned spaces during certain hours. If we were troubleshooting, let's say, extremely high airflows or even high fan energy usage, we can first start here and see what is driving the high airflow. Is it the load? Is it the supply air dry bulb, which is reported in the top right-hand corner? All the information about the design of our system, as well as the building loads, are shown all in this report. Additionally, from an input standpoint, we can see drastic changes in results by the scheduling of internal loads. It is best to create custom schedules for people, miscellaneous loads, and lighting to be reflective of actual building operation in order to apply diversity to the system if it allows it. To jump back into the results though, the supplier dry bulb temperature and cooling will be output in the top right-hand corner, and the space temperature we'll have to determine based on our own inputs in the crate rooms or template section of the program. Trace determines the supplier dry bulb temperature through a psychrometric calculation using the building loads in conjunction with the system type. We will not be going over that calculation today, but we have more information in our Trace 600 engineering manual that discusses that calculation. And we'll also be looking at the psychrometric report later on, so we can kind of dig into it. However, if you were to fix a supplier temperature, you could potentially see over-undersizing for your system type located down here. Essentially, you're telling the program what the size of the cooling coil has to be, and Trace is going to calculate what it should be based on the psychrometric calculation, which is where you're going to see that difference. In this case, based on looking at the right-hand side of the outputs, you will see that we have roughly 40,000 CFM calculated for our main fan airflow. However, there are other airflow outputs as well. Based on the system type or inputs modified, you may see different airflows for the diffuser and terminal from the main fan airflow. As an example, if there is duct leakage, you can see some of the terminal and diffuser airflows change. Or, if there is a secondary fan, which is essentially a terminal box fan from either a parallel fan powered or series fan powered system, then airflow will appear under the secondary fan category. Here's a good time to mention F1 help. If you are unsure about what a specific output may mean, you can press F1 on your keyboard, which will bring up the appropriate description of most of these line-by-line items. If we get back to the report, in heating mode, the airflow is calculated based on the system type selected. If it's a VAV system, the heating airflow is usually the minimum stop, which is 30% of the cooling design airflow, or the ventilation rate, whichever is greater. However, if it's a constant volume system, the airflow will be identical to the cooling airflow. We do not perform a secondary psychrometric analysis to determine the heating airflow. If you're curious on how the heating airflow is calculated for certain system types, the user's manual or Trane 700 output interpretation manual will give you some examples of different system types. In addition to the airflow, the supply air temperature and heating, shown below here, is calculated based on the total heating load and the resulting airflow as discussed earlier. For certain system types, supply air temperatures are defaulted to certain conditions, such as 125 degrees F for a parallel fan powered system. And as said before, use the appropriate reference materials or contact our support team for more information. Next, we can take a look at the cooling coil selection information. This will show us the total capacities of all of the coils in our system. The main cooling line item here is meant for the main coil, which conditions the space or spaces to the thermostat set point. If you had a dedicated outdoor air unit, it would be under the optional ventilation line item here. And if you had a chill beam or other auxiliary coil, it would be under the auxiliary cooling line item here. You'll see total capacities, sensible capacities, coil airflow, entering and leaving conditions off of the coil. So in our case, you'll see that our main cooling coil is at roughly 110 tons. One thing to mention here is that the airflow for your cooling coil is calculated based off of the space sensible loads at the coil peak, which is listed right up here, whereas the airflow on the right-hand side of the page is calculated based on the space sensible loads at the space peak, which is this line item right here. So you may ask the question, why does the space and the coil peak at different times? Well, usually the glass solar is going to drive the space peak, while the ventilation or system type loads is going to drive the coil peak. In general, though, you can select your fan airflow based off of the design airflow on the right-hand side of the page, since this is the airflow required to meet the thermostat set point. However, if you are concerned about dehumidification issues, since a higher airflow may not be able to wring as much moisture out of the air, you can always select a supply airflow that is somewhere between the coil airflow and the design main fan airflow, but it is a design consideration that you must make in that case. Let's talk about some troubleshooting real quick though. Let's say we have unmet load hours. In this section here, we can check the coil sizes and make sure they aren't undersized through the undersized line item here in over and undersizing. Remember, in cooling, negative means undersized, while in heating, negative means oversized. Moving back to the cooling coil selection, for the entering conditions of the coil, these values are calculated based off of the mix of return and outside air typically. For the leaving supply air dry bulb temperature, this is calculated through psychrometrics. However, for the wet bulb and humidity ratio, these are calculated not through psychrometrics, but by a delta enthalpy across the coil. If you are interested in seeing what a generic coil curve would generate for leaving wet bulb and humidity ratio, look at the psychrometric state points found in the psychrometrics report, not in this report. We'll talk about how this is important later on when we are discussing Trane 700 versus what happens in the real world. Finally, we can take a look at the heating coil sizes. In this situation, we are looking at the system checksums, so the preheat coil would only apply to this report. How did I know this? Well, look at the schematic for the system type chosen from Create Systems. You can see here that we have a preheat coil on the system level. And so this schematic is going to give you a clue to where the coils are located. Now, if we wanted to see, what the terminal box reheat coil sizes are, we would want to look at the zone checksums, which will give us a zone level output. What's important here in general is that we need to look at information that is relevant to the system we have chosen and the inputs we have modified related to the output. The checksums is a catch-all for outputs where some items may or may not necessarily apply. Trace also makes assumptions based on the ASHRAE fundamentals books as a guideline on how certain coil sizes are calculated. They may not be exactly what your methodology is, so call into our support center if you have questions regarding Trace's calculations. Moving on, we can head to the psychrometrics report where we can take a look at the specific outputs relevant to our cooling coil. In this case, we have a system level cooling coil, so only the system level report is available. This is where we can view the different state points and plot them on a psychrometric chart if we wanted to visually view the outputs. Here we can see what our space condition is, which is 75 degrees, and the resulting relative humidity, which is 50.2%, as well as the calculated supplier temperature of 60 degrees and the sensible heat ratio, which is 0.88. We can then make a judgment call on whether or not our SHR makes sense based on our inputs, as well as the resulting dry bulb and wet bulb conditions off of the coil. What's great about this report is the ability to dissect an air system and interpret results for either troubleshooting or optimizing a system. It could be a situation where we need to look at the ventilation state points so we can see what the outdoor air is and entering into the outside air preconditioning to see if we maybe need an ERD or if we had an ERD if it's properly preconditioning the outside air. Or we can also take a look at this report and see, okay, well, what is the resulting relative humidity? Do we need further dehumidification to remove more moisture out of the space or spaces? Lastly, we can take a look at the system component selection report. Here, this report will show us how many coils, fans, and systems we have in our particular building. It also gives us total coil and fan sizes, so we can use this for a selection process. Like I said before, it's easier to read than the checksums and gives us more relevant information. If we were selecting equipment looking at the cooling coil information here, the questions to be asked are, can we get a rooftop unit in the size of 110 tons based on the airflow and the entering and leaving conditions? Are the entering conditions realistic? What about sensible and latent capacities? These are all important questions when looking at this type of report. Additionally, maybe certain manufacturers can't give us electric heating coils in a VAV box that are these sizes. So we might need to introduce more VAV zones for this particular building. In general, though, this is a great report to use from an equipment selection purpose. Now that we've seen an example, let's spend a little bit of time talking about some output considerations that must be made after analyzing a Trace 700 load design run. The output from Trace doesn't necessarily relate to what can be done in the real world. Additionally, the level of accuracy is up to the modeler and how much effort is put into the load design. This is what should be considered from a theoretical versus applied consideration. For all conventional systems, Trace assumes a space is well mixed. However, in reality, even in a standard VAV system, if the system isn't designed properly, air from diffusers may not reach all areas of a zone, which can lead to higher or lower space temperatures than expected. Another example is thermostat placement. Trace doesn't have an input for which wall a thermostat is placed on, which can impact predicted loads as well as energy usage. Remember, all software programs have assumptions, so one has to go beyond taking outputs from Trace and assuming it matches exactly what the building design contains. Speaking of system types, Trace has a variety of standard system types that are used in many buildings today. However, there are a lot of special cases out there that don't fit the mold of what Trace has to offer. Even if you choose a system in Trace that has some characteristics of the intended design, this does not mean that the output will be close to the actual performance of the system. A few examples, such as using baseboard heating for main heating source, or even radiant cooling instead of a conventional overhead type of system, can be done in reality, but Trace has some limitations in modeling these scenarios. If you're ever in doubt, consult with CDS support for more clarification. And lastly, Trace assumes the entire space meets the set point temperature in load design. In reality, this may not be the case, so it's important to think about this when running load design calcs. With that in mind, various manufacturers may not be able to produce a certain type or size of equipment as well as generate the same performance or design criteria as shown in Tray 700. As such, results need to be thoroughly analyzed and discussed with the manufacturer to determine if what is proposed is even possible. Trace does not know many variables that can impact a building's mechanical system design. From a selection standpoint, the output that Trace provides for equipment is only a guide and should be treated as such. This is because the coil curves for various equipment and manufacturers can vary significantly depending on several properties, such as fin stamping or material surface of the coils. Trace uses a generic coil curve algorithm that in most cases will provide the engineer the information necessary to make the proper equipment selection from a manufacturer's selection tool. Overall, though, it's an iterative process working with the manufacturer's selection tool and then modifying the load design inputs to appropriately select the mechanical system for a building. This completes our discussion on load design output interpretation. Hopefully we've given a basic understanding of the load design outputs in Tray 700 and how to use them. If you need some assistance in other areas of the program or just want a better understanding of some of the concepts we talked about today, here are some additional resources available to you. As always, please feel free to contact the CDS Support Center by phone or email with any comments, questions, or modeling issues you may be experiencing. Thank you for your time and happy energy modeling.